Hi, in this video, we'll talk about some of the problems that we can solve using the algorithms built in natural language processing domain, like word sense disambiguation and information retrieval. So before we move on to some of the problems, we'll talk about a basic NLP model that usually helps in solving all such real world problems. That is the language modeling. The language modeling is nothing but a statistical model which assigns probability for sentences. You can consider sentence just to be a sequence of words for this particular example. We don't have to follow, let's say, grammatical structure, but you can just consider it as a sequence of words. So the modeling of language is about assigning probabilities for such a sequence of words. And the probability can be for the sequence of words, and it also can be for the words themselves. For example, in the sentence, I am staying in Mumbai, we would calculate what is the probability of the word am, I, in, and thereafter we could also calculate what is the probability of am followed by I, in followed by am, and so on. We'll get to see how exactly these probabilities are calculated and why do we need to calculate them in a minute. So before we look at how we build language modeling algorithms, let us understand why do we need language modeling, where do we apply language modeling. One of the most common application is a machine translation task. The task of machine translation, so if you go to translate.google.com, you might have seen that this tool can translate a sentence from one language to another. So let's say I have entered a sentence, मैं मुंबई में रहता हूँ. If I give this sentence as my input, it would identify this language to be Hindi, the script to be in Hindi, and now the task is to convert this into English. That is the task of translation. When we translate, we convert the sentence from one language to another language, and when we automate that task, we call it as machine translation. So, given this particular sentence in Hindi, now I have a probable sentence which says, I am staying Mumbai. So what I do is that I have a full list of sentences in natural language processing domain. Whenever we talk about a data or a combination of a collection of sentences, we call that as a corpus. So I have a corpus of sentences, and now I try to calculate what is the probability of two of my probable translations. So I have one probable translation as I am staying in Mumbai, the other probable translation as I am staying Mumbai. So given these two probable translations, how would I rank them? How would I assign what should be the right translation? And that's where the language modeling kicks in. And it says that we are not very sure that I am staying Mumbai is the right translation. We can replace that choice with I am staying in Mumbai based on the corpus of sentences or the collection of sentences. That is one. The other application is a language generation, which is nothing but we detect grammatically correct sentence, same as above using probabilities. We can also generate languages, or let's say I have typed I am staying. We can also generate such kind of sentences altogether using language model. So just to give an example of how language generation looks like, I would suggest you to look at this model called GPT-2 that was recently published by a company called OpenAI. So in the recent past, there has been a lot of research, especially in the natural language domain and especially in language modeling aspect, where we are trying to understand how we can generate entire new sentences, having seen lots of text that is already lying around across the internet. So they use the Reddit data, I guess up to 40 GB of data from Reddit, and they built a language model. Now with this language model, they are able to generate entire articles, entire a piece of blog post from just a language model itself. You should go and check it out and see how well the current systems can actually generate languages. So other applications being spell correction. Like in this example, take a right turn or a left turn. We can clearly see this right, even though it is a correct spelling, is not the right word in this particular context. as we are talking about turns, we can say that this particular word should be written as RAGHT instead of WRIT. So spell correction can be solved by language modeling. Other thing is word prediction. So whenever you are using google.com, whenever you're trying to search any phrase, you might have noticed there's a completion that is coming at the end of your search query. So how does that happen? So we're going to study that in a minute, but the domain is called as word prediction, where given a set of words in a sentence, we try to estimate what might be the next word. So if you have given me the query like I am staying, I might have the next probable words as in, and, where, etc. So the probabilities of these words in the sequence are calculated and sorted in the decreasing order of the probabilities. So now that we have understood what are the applications, we'll see how we can build such a language model. One of the common approaches that is followed in this research of language modeling is an n-gram approach. What n-gram says is, let's say given a sentence, let's say I'm staying in Mumbai, all I need to calculate is what is the probability of seeing that sentence given a corpus of sentences, given a collection of sentences. Now, this sentence can be broken down into a sequence of words like W1, W2, W3. Each one is a word, single word here. W1 is a word, W2 is a word, and so on up to Wn. Now, what I can do is I can calculate what is the probability of observing this sequence of words and assign that as a probability of that particular sentence. This is my task. So what I can do from my probability theory is that I can calculate this joint probability. Let's say I have two variables A and B. I want to calculate joint probability. I can say probability of B given A into probability of A. And if I have multiple of them, I can just add those multiple terms here and then keep on repeating this step. So that's what the next logical step that we can do is that what is the probability of the word n having seen all the words so far till n minus 1. So if we can define that, then we can convert this joint distribution into two terms, that is probability of word n having seen all the words so far into probability of seeing the word n itself. This would solve a problem for calculating the probability of sentence. And the above definition is also used to predict the next word, the one of the applications that we have just discussed. And both the definitions can be determined using n-grams. A sentence can be represented by n-grams. So what are the possible ways that an n-gram can be represented as? We can represent these n-grams. I'll discuss what exactly is n-gram in these variants, where we can have a unigram, we can have a bigram or a trigram or 4 grams and more. The gram here is nothing but the words, or you can consider as the units of the sentence. And if you're talking about the unigram, then we are trying to model this particular language, this particular joint probability as a combination of individual words. If you're talking about bigrams, we are trying to model in terms of 2 words at a time. So let us just get into exact details. What do I mean by unigrams and bigrams? So unigrams is nothing but considering each word as an individual token. So let's say we have an example. This is an example sentence. And from the sentence, what we first do is generate all these n-grams. Right now, we are only interested in unigrams. So what do? Uni stands for 1. So I generate all the single words from my given sentence. That will be this is an example sentence without any order. So now I have a set of individual words. Now when I want to calculate this probability of this sentence, what I would do is I translate this into my sequence of words, and as I'm using a unigram model, I would simply calculate probability of word 1 into probability of word 2 to probability of word 3 into probability of word 4 into probability of word 5. So because I'm relying on a unigram model, so how do I calculate this individual probabilities of word? Individual probability of word, let's say this, I want to calculate the probability of word this. I'll just look at the entire corpus, the entire collection of my sentences that was given to me as a training data, and then I just count the number of times this this has happened, and I also divide by the sum of count of all the words. So let's say this is word. I take the sum of all the words as a denominator, and then I find what is the proportion of seeing this word among all the words. This is how I calculate the probability for seeing a word in a unigram model. For this example, if my corpus is only this sentence, I have 5 words in total, and this has seen only once. The word this is seen only once, so my probability of this is 1 by 5. So coming to bigrams, which is a natural extension where we are trying to model 2 words at a time. Now with the same example, I can have bigrams like this is an example sentence. So we have 4 bigrams. In the previous model, in the unigram model, we had 5 entries in the set. Now we have 4 because we are going with a bigram. So now the question is, how do I calculate the probability of the word I given word I minus 1? So why we are trying to do this? Again, if we come from the probability of the sentence, this sentence can be calculated as probability of all the words. And as we are using a unigram model, what we are suggesting is that I'm going to calculate the bigram probabilities, the conditional probabilities of a word given the previous word. So this is what I'm trying to calculate in my language model. Here, if you see the probability of W5 given W4, what it says is that in all the instances where I have seen example, how many times has sentence appeared in the next place. So if there is another sentence where example is followed by good, and then there is another possibility of a sentence in my corpus, example followed by bad. Now we have 3 such instances of example, but only in one instance I have seen the word sentence that is appearing after example. So now my joint probability would be calculated as how many times I have seen example and sentence divided by how many times I have seen the word example, because we are calculating what is the probability of the next word given the previous word. So that will be, it is only seen once, where in this hypothetical example that I have given here, we have seen example 3 times, so it will be 1 by 3. Similarly, for calculating higher order n-grams, we need to have a larger corpus. So if you want to extend it to a trigram, this will be simply that you want to calculate W5 given W4 and W3, and you want to calculate the probability of W4 given W3 and W2, and similarly you want to calculate this trigram probabilities. Probability of the sentence now is calculated in a trigram model. So this keeps on increasing as and when you increase the n in your n-grams. However, what you need to observe is that such kind of probabilities, whenever we keep increasing the n-gram, will have lower values because it's very, very less often to see such a combination in our corpus. A unigram can be seen often where the individual words can appear by themselves, but if you want to see that W3 and W4 and W5 occur in the exact same order, we would have very sparse probabilities in our model, and sometimes these probabilities can be as low as 0.001. So we would end up with a lot of issues when we go into higher n-grams. And also the other problem we might have is that if you are trying to build this language model on one kind of data, let's say you are using literature data, and then you have built this model, now you are given a news corpus. If you try to test this model on a news corpus, then it will fail pretty badly, because in the news corpus the way the words are distributed are quite different. Compare that with the literature data. So we also need to be sure on what kind of data are we training and what kind of data we are testing on. So for calculating the sentence probabilities, we will use a chain rule like probability of sentence. It can be used as probability of W1 into probability of W2 given W1, and we keep on doing till probability of the last word given all the words so far. For this example, I am staying in Bombay, and now we can use this chain rule to calculate the probabilities of we have a unigram here, we are using a bigram here, we're using a trigram, and we are using a fourgram as well here, to just to give an illustration of how exactly it has to be done. However, we take a lot of assumptions. Let's say if I want to go only with the bigram, then I can just have this. If I want to go with the trigram, I can only have this. So based on these n-grams, we can now calculate what is the probability of a sentence like I am staying in Bombay, and what is the probability of sentence like I am staying Bombay. And then we can compare these two probable sentences and then weigh what is more probable sentence based on the data that we have seen. When we start with a higher gram language model, what happens is that, as I was mentioning, it's very less common to see anything of this sort where all these words should appear in the same order in our corpus. So whenever that happens, whenever we don't see any such data, we follow what we call as a back-off model. So let's say we started with a 5-gram model. In case of less amount of data, what we do is we just back off to a lower n-gram. From the 5-gram, we just back off to 4-gram. So we calculate probability of W5 given, let's say we are using a 4-gram here, we are backing off to a trigram. So what back off says is that whenever you don't have data, whenever you have less data, it is better you back off to a lower n-gram and calculate your conditional probabilities. You have to repeat this until you get good amount of data so that you can calculate this n-gram probabilities. We also call it as stupid back off. There is not much of logic involved here. So the other way of solving for the sparsity in our data is to have interpolation. What interpolation says is that we can mix language models. So when we don't have enough data for higher n-grams, we'll look at all the possible unigrams and trigrams and bigrams, and then we mix them together so that wherever we have less data, we can get the probabilities from the lower n-grams. So interpolation is usually done to enhance the behavior of the language model, and there can be weights that we can assign to each of these n-gram models, saying that for the task of machine learning, we can give more weights to the bigrams and trigrams and less weights to the unigrams, because the translation requires a grammatical structure to be intact. So maybe we can give more weightage to the higher n-grams, whereas for spelling correction, we can give more weights to the unigrams rather than for trigrams and higher n-grams. Smoothing is one other technique that is used. Whenever you have very sparse data, you might end up with probabilities being undefined. So smoothing is just making sure that wherever you try to assign probabilities for unseen data, how will you solve for such probabilities? There are some simple techniques that we are not going to discuss in this lecture. However, these are nothing but we tend to add a simple value like +1 for all the words which we never see. Let's say we have a corpus on news, and then we are given a new sentence from literature. We don't see a word from this particular sentence. We just add +1 for all the words we have seen in news as well, so that we don't end up with undefined probabilities. That's a basic concept of smoothing, but we won't be going into the details of it. So one of the applications of natural language processing in understanding human communication is word sense disambiguation. What word sense disambiguation says is that every word can have different meanings in different contexts. So let's say I have two examples. I say I withdraw money yesterday from the Kotak Mahindra Bank. I use the word bank here. And then there is another sentence where I say I spent my time playing with friends on the banks of Narmada River. If you have observed keenly, then we have an usage of the word bank in two different contexts. Even though the word is the same, the context has changed the meaning of this word completely. So whenever we have such a case, we call that as a word sense disambiguation. That means we need to understand the meaning of a word based on the context. Why is this important? Whenever we want to retrieve relevant documents, let's say in Google you try to search Apple CEO, then the results should be ideally talking about the company Apple rather than the fruit apple, because apple can be having multiple meanings. It can be talking about a fruit, or it can be talking about the company Apple. So how do we how do we disambiguate whether this particular query is about the company or the fruit based on the other words and based on how the previous results were? We can disambiguate that this apple is talking about company, so I should show results of the company apple, not the fruit apple. Machine translation, whenever let's say we have sentences like I love playing with cricket bat, and another sentence I'm afraid to go to the cave because of bats. So whenever we have a similar word used in different contexts, and if you want to convert into the language, we have to be careful that we should not convert the word bat just based on the word itself. We have to look at the context and then take the right meaning of this bat. Only then we will be able to translate into the language with accuracy. So before we try to see how to solve word sentence ambiguation, we need to first understand what are the different senses, what are the different relations we can have between two words. We'll get into detail exactly about each one of them. Let's start with the homonyms. Homonyms are the words that share a form but are unrelated or having distinct meaning. Like in our previous example, we have two different uses of bank or two different uses of bat. So wherever we have a semantic meaning which is in context with the sentence, but the word looks the same, but word is written the same and is pronounced the same, we call that words as homonyms. There are some certain subcategories of homonyms as well, like homographs. Homographs are words which are spelled the same and may not be pronounced the same. Like when you're talking about tear or tears. Tears is something that we refer as water from eyes. Tear is something that we rip a paper, but it is spelled the same, it is written the same. So such kind of words like bear also is a homograph. So such kind of words are called homographs. And then there's other subcategory, homophones. Homophones says that the word spelled differently but the pronunciation is the same. Like right and right, peace and peace, they are pronounced the same but they're spelled different, they are written differently. Such kind of words are homophones. And then we have different category of words called polysemous. Polysemous words have related meanings across sentences. So if you look at these examples here, I want you to keenly observe the word over that has been used in various different contexts across sentences. For the first sentence, the picture is over the sofa, where in this sentence the word over is used in the context of above. It is suggesting that the picture is above the sofa. Whereas in another sentence the picture is over the hole. In this context the over is a word which is trying to suggest the meaning covering. So the picture is covering the hole. Similarly, there are different contexts that are being used for the word over in other examples. So such kind of words which have different meanings across sentences are polysemous. Metonymy are the words having related meanings across sentences but preferably in the same domain. This is quite interesting. So let us look at these two examples. The first example says, the bank is colored in blue and white. The second one says, withdrawal from money from the bank is pretty easy. Here the word bank again appeared in our example, but if you see, both of them are referring to the same concept, a financial institution, but in the first sentence we are referring the bank in the context as a building. We are referring bank as a building, whereas in this second sentence we are referring it as a financial institution. So they have been used in the same domain, that is they are talking about a financial domain. However, the way they are used is different. Such kind of words are called as metonymy. This relation is not just the bank. There are also other sentences where there's a correlation between building and organization, like hospital, school, office. So there are other words which also have such kind of a multi-use across sentences. So one other example is when we talk about author, and we usually refer to the works of the author. Like let's say Jane Austen has wrote Emma, and if you say I love Jane Austen, that doesn't mean that you actually love the person Jane Austen. You love the work of the author Jane Austen. Metaphors are the words which has similar sense of meaning but expressed in different words. You might have come across a lot of metaphors, so I don't have to brief that about. So, for example, I am on top of the situation, she's at the heights of power, his power rose. These are the words which has similar sense, but they are expressed in different combinations of words. They all try to sense that there's a power of control that is being conveyed here. Synonyms are the words which have the same meanings but are different words, like big and large are synonyms, but not in all contexts. However, big glass and large glass have the same sense, but big brother and large brother doesn't have the same sense. So, even though some words are called synonyms, it also depends the context in which you are using them. Antonym are the opposites. So, examples like short and long, in and out, all those words which have opposite meanings are called as antonym words. Hyponym is a subclass relation between words. Like if you say car and vehicle, if vehicle is a class, then car can be considered as a subclass or a subordinate. So in another example, mango is a subordinate for the class fruit, and similarly mobile can be a subordinate to the class electronics. The relation between two classes can be represented in the form of a is a relation. So such kind of subordinate classes are called as hyponyms. That means vehicle's hyponym is car. It is a subordinate of the class vehicle. And some of the instances of hyponym are like iPhone is a mobile, mobile is electronic. So what is the difference between the relation of words in above two sentences? iPhone is an instance of the class mobile, and mobile is a hyponym of the class electronics. So when there is a relation between two classes, then that is hyponym. When there is a relation between a class and entity, it is an instance of class. So if you remember from the semantic nets that we have discussed earlier, we have discussed that we can have classes which can have a relation of is a, which means that this class is a subclass of this class. And then we can have objects, like in this class of mobile, one of the object is an iPhone. Such kind of objects would be connected with an instance of relation. So once we understand this concept, we can say that only the subclass relations are referred as hyponyms, but not the instances. Hyponyms is the opposite of hyponym. When we say mobile is a hyponym of electronics, then electronics is a hypernym of mobile. The reason we have discussed all these various relations is to introduce you the concept of a word net. The word net is a repository of words along with their relations. So if you remember your class on semantic nets, word net is a perfect example of a semantic net which has all the words from the dictionaries, like bank, and there's a bank which is have a financial institution sense, and then there's a bank which has a sense of river and water bed. So there are different senses of the words which are connected with some relation, and then we have the parent relations, hyponym relations, which has like financial institutions, and then we have other relations like instance, where we are talking about a specific bank, maybe like HDFC. So we have several words that are used in common language, and all of them are represented as nodes and edges along with what the relation are. Is there a synonym? Is there an antonym? Is there a hyponym? Hypernyms? What are the all possible relations of this particular word? What are the relations it has with other words? So all of this is combined and put together in a software, and this is very often used in NLP. If you want to apply any model in NLP, the first thing that you come across is a word net, and you have to be familiar with this concept, and that's why we have discussed all these relations, which will help you in understanding word net much easier. So you can see the demo of a word net by following this link here. And also word net supports not just English but other languages as well. So each word in word net has different senses of usage. It also has synonyms. in each sense, by the way. And the hierarchy of the word till the abstract level is also present. We have member of relations, we have it has member relation, we have part of, has part. So we have multiple relations for each word, and we also have what are the words that are related to this with this particular relations. So using this relation between words, we can define the sense of the word in a particular sentence. Now let's come back to the problem of word sense disambiguation. Now that we have understood that there's a software, that there's a thesaurus like WordNet, how can we solve this problem using WordNet? So let us calculate the correct sense of the word given multiple word senses referring to the WordNet here. So example again, I played with my cousin on the bank of river Narmada, and I have withdrawn my money from savings account of that bank. So in order to disambiguate the sense of bank, we have to calculate the similarity scores between all the words that are in the context of the bank. Like river and bank are in one context in the sentence 1, and bank and account are in a context in the sentence 2. So how we do that is that, let's say for the sentence 1, I'm calculating the similarity between bank and river. And the way I do it is I take the similarities of all the different possible senses of these two words. Let's say this has 5 different senses. We can refer that in the WordNet. Let's say river has 4 different senses. And for each possible combination of these two senses, what is the similarity score? We'll define what is similarity in a minute. Once I take all these combinations and find all the similarity scores between these combinations, I take the maximum of it, and then I assign that as a similarity score of words bank and river. The way we calculate the similarity between two words for a particular sense. So let's say for the financial bank and water river, we calculate the similarity by the path length of these two words of those senses. So as I said, the WordNet is a big semantic net. So if you want to reach one word from another word, you would definitely can reach by following a path. And if you calculate the length of this path, it will tell you a sense of how far these two words are. If you want to understand the distance between two words, you can also calculate the path length. So that is what we are using to calculate the similarity between these two words, bank and river. And we are looking at only a particular sense of these two words, so that we will get exactly which two senses are closest to each other. So the path length is calculated as 1 plus number of edges in the shortest path in WordNet between bank and river. So from the meaning of bank, sloping land on the body of water, river has an hypernym as body of water. So based on the above two measures, the path length of bank and river can be 1 plus 2. The number of edges that would need from moving from bank to river can be 2, and we have a path length as 1 by 3. So in this context, the similarity will be 0.33. Similarly, to calculate the similarity between bank as financial and river, once we see the WordNet, we'll get to know that similarity is 0. We don't have any path. So now that we understood that there is no relation between this semantic sense and the semantic sense of river as water, we can eliminate this sense, and we can consider the bank as a sloping land on body of water and associate that with river. And using WordNet is one approach. We can also use an n-gram approach. So what we can do is we can use the bigrams and trigrams that we have studied earlier to get the context of the word. Using this context, we can expand the word with synonyms, and then we can see based on what are the contextual words like river and bank and maybe a picnic. We can understand that in this context, bank is referring to a river bank. So that is about word sense disambiguation. We'll look at another application of NLP, which is much more heavily used in our everyday life. That is the information retrieval. So you might be using Google like every 3 to 4 hours or every day or maybe every 2 days. But it is obvious that we can't live without having an internet search engine these days. The reason is because we have so much of unstructured data in the entire internet, and we need to figure out a way of navigating through such unstructured data to get to the exact information which we want for that particular query. In order to do that, we have an entire field that is being populated, which is called as information retrieval. This is nothing but to retrieve relevant information from large collections of unstructured data. So the amount of content you see in internet is what we refer as unstructured, because there is no agreed structure to any of this data. Some might have PDF, some might have paragraphs, some might have images. So there is so much of information that is floating around in different structures. So when you have such a large collections, how can you find the relevant content? We will try to get there using this field of information retrieval. And we have other searches apart from simple Google text search. We have music search. We can also do image search as well. So even there, we will be using the concepts from the field of information retrieval. So how information retrieval works, let us first understand that in two parts. Let us see that information retrieval first handles all the data that we have in the internet. Using all the unstructured data and using the techniques that we have in information retrieval, we would build something called as an index first. Before even we start serving any queries, we'll first build an index. Once we have done this step, then we can open up our search engine to users, where users would give us queries saying that this is what I would like to get an answer to. Then we can use the index that you have built already and have our ranking systems in place, and so that we can show the relevant documents to the users. So we have a two-step approach of solving information retrieval. Let us look at a very basic system of information retrieval, which we call it as Boolean information retrieval. Let's say there are 3 documents and each document is only having one sentence. It's a very simple example. Most often we have multiple sentences. So here we have 3 sentences. First sentence says Delhi is India's capital. The second one says India is the fastest growing economy. And the third one says Delhi has many cuisines. Given these 3 sentences, the first thing that we'll do is construct a term document matrix. The reason we call it as term document matrix, because we write all the unique terms as rows. These are all the unique terms from the 3 documents, and we denote the documents at the columns. This is document 1, this is our document 2, and this is our document 3. However, we have only one sentence, but for the illustration purpose, we are calling it as a document. So given this particular document, given the terms, what we'll do is we'll just put a 1 wherever this term appears in that document. So India is present, so we just put a 1 here. Delhi is also there, we just put a 1. We can see the word is. There is no fastest, there is no cuisine. I can see a capital there, and there is no growing word as well. So I do that for the rest of the documents as well. And then what we have is a term document matrix where it is filled with 1 and zeros, 1 saying that that term is available in this document. Given this term document matrix, now let us say I have a query which talks about, I need to find all documents which talk about Delhi and India. What I do is I first get all the documents that are talking about Delhi in a Boolean format, which is in document 1 it is there, so it will be 1. In document 2 I don't see a Delhi, so it will be 0. In document 3 there is a Delhi again, so 101 is my Boolean representation of the word Delhi. And similarly I do it for India, and I simply do an AND operation on top of these 2 Boolean queries, Boolean vectors. When I do an AND, I'll be ending up with 100 saying that I can see Delhi and India in the first document, but I don't see both of them occurring together in the rest of the document. So it says that the relevant document to be retrieved is the first document only. So this is a very simple example on just 3 documents. Imagine we have 1,000,000 documents with 1,000 words each. So let us assume the unique word count is up to an approximate of 500k. Then our term document matrix would be of the size of 500k into 1 million, 1 million being the documents. So that will be around 0.5 million trillion entries. That will be the size of the matrix. The maximum entries with value 1, however, can be only 0.001 trillion. Why? Let us assume each document has 1000 words and all the 1000 are very unique, that they're never seen across other documents. Even in that case, if you take 1 million docs and 1000 words, unique words in each doc, we would only get up to 0.001 trillion entries in this particular term document matrix. However, we are having so many entries in the matrix. That means we have such a sparse representation, such an inefficient representation. So we can't use such a Boolean information retrieval system for real world systems. Instead, what we will do is we create an inverted index. So that is the next logical step from term document matrix. Now we have represent this term document matrix. I'm not going to use this term document matrix, having seen the space requirements that I would need. So what I do is I'll take the word and I simply write all the document IDs where this word is being seen. I can see this word appearing in document 2 and then document 4 and document 5, and similarly I do this for the rest of the words. This particular linked list is what I call as a posting list. In the information retrieval terminology, we call it as a postings list. So this is a very simple inverted index. I do this for all the words and I then index that somewhere. So the steps that we follow for creating such an inverted index is that we first collect all the documents that we want to be indexed, that we want to be searched. Once we collect the documents, we first tokenize them. That means we first break them into individual tokens or individual literals, that is nothing but the single words. And then we do linguistic processing. We will clean the words, we'll remove the non-informative words. We'll do a little bit of NLP steps. I'll discuss that later. Once we have done with the cleaning of the words, we will index them in an inverted index fashion that I just described. So, if you take an example of two documents, document 1 is I am new to India and document 2 is India is having many cuisines, we'll just convert all of them into tokens. We'll look at all the doc IDs where they are appearing. And then what we do is we take the term, we write number of documents that this word was seen in along with the posting list. This is a posting list. It says I can see the word India in document 1 as well as in document 2. And whenever I have a query like India and cuisines, I'll get those posting lists and I'll merge those two posting lists, saying that in document 2 I can see both India and cuisines being talked about. So, however, this only says that whether there are words in this document or not. It doesn't give you a ranking of all the results. It doesn't consider the frequency of the query terms in the documents. What if there is a document which talks about India a lot, but the other document that I suggested only mentions India once? So I want to understand how frequently these query terms are being talked in the documents so that I can rank them. The frequencies indicate the degree of relevance. This is a very important criteria for me to rank my resulting documents. And the Boolean IR displays retrieve results without any ranking order. They just say, hey, you gave me this term and these are the documents I can see clearly have a mention of this term. And that is all that I can give you. So in that case, browsing the documents will be very painful when you have results in the tune of thousands. So in order to rank the documents, what we are going to use is something called as a TF-IDF score. A TF-IDF score says that given a query, I will retrieve, let's say I have retrieved 10 documents using my traditional Boolean IR or maybe the inverted index. Now my task is to rank them, how relevant they are to this query. What I do is I look at all the terms in this query and I count each of those terms for each document and assign a score. I'll assign some score for each document, saying that how often or how frequently these words are seen for that document. So what I calculate is a score for the query and the document pair. For every query document pair, I calculate a score. It is a function of the frequency, the term frequency we call, of each term of the query in the document, and also it is a function of inverse document frequency of the term T overall. So now that we have seen what is the term frequency is nothing but how many times the term T in the query is appearing in the document D. Then what exactly is inverse document frequency? So if you see many common words like a and the, they often are seen in across all the documents. If you carefully observe, very few documents would not have such a common words. So what does it say is that if you have words across all the documents, then they are not important for me to rank my search results. I should reduce the importance of such words based on the number of documents it is seen in. So if I have 1000 documents in my corpus and let's say A appears in 900, then I can clearly say that it doesn't really matter if A is matched or not. It doesn't carry any significance in ranking my results. So based on the frequency, the document frequency of the word, I reduce the score of those words which are matched. So inverse document frequency just says that I take inverse of the document frequency. So let's say I am calculating for the word T. I look at the word T in the entire corpus, in the entire collection, and I calculate the document frequency of it. And then I take the total number of documents in my corpus, N, and I divide it so that the higher the document frequency, the lower the overall value. I take a logarithm of that, and that is what I am referring it to as an inverse document frequency. So having calculated the term frequency and inverse document frequency, I am now able to give a score for each query document pair using this formula. I do it for every term in the query. So let's say query has 3 terms, T1, T2, T3. I calculate this TF-IDF for each of those terms and then I sum it up to get me a final score for that query document. So before we come up to the ranking, as I was mentioning, we have a list of linguistic processing that we have to do before we create the inverted index. The first step is the tokenization. Tokenization says we just need to extract tokens from a sequence of words. Let's say we have the sentence, we have different cultures in India. We will extract each individual tokens. This looks pretty simple, but if you look at it, we would have multiple problems, like there might be joint words, or there might be, especially in the Chinese language, we don't have the space anywhere between words. So how do we take that entire piece of text and convert them into individual tokens is a challenge based on the language. We will also have certain challenges in English as well based on the complexity. So tokenization is a simple but still required step to convert a sentence into a set of words. Second thing that we have to do is stemming. If you want to match, let's say, the query term culture with the word cultures, so there is a document. So there's a document D10 which has a mention of cultures, and you are trying to search for culture. However, the words are similar. There is a plural and a singular form of them, so they won't be matched if you use it as it is. So what we do is we convert such words into the base form. So let's say cultures is now converted into the base form culture, and then you also convert your query term into the base form so that you can match these words as well. So after tokenization, we do stemming, and then we do stop word removal. That is nothing but all the obvious terms like a and the of are removed from the query as well as the documents, so that they won't add any noise to our process. We also do some spelling correction, like if you have any misspelling words in your document or in your query, we correct them up. And also we can do auto completion, assisting a user while possible such query completions. Like in Google, when you're typing, let's say Sachin, the Google might suggest you are you searching for Sachin Tendulkar. So the auto completion would also help us in improving our query efficiency. Also, sometimes we would like to search for a semantic match. Like if there is search for thermodynamics, we would like to also match with heat when we have a document that is talking about heat. So another example is when you're searching for aircraft, you also want to get relevant results for plane. So all this comes under query expansion, where we keep on adding related words for each of the queries so that we would able to serve such purposes. Thank you. And in our next session, we'll talk about anatomy of building AI systems.